All right, let's get started. Hope everybody had a good weekend. The semester is giving us like this sensation that it's almost over, but it's not almost over. And this is the one thing I don't like about the fall semesters, that we get real close to Thanksgiving and people start, just, man, here comes the turkey, here comes the cold weather, here comes the football and all that. And they forget that they register for a 16-week class. So we are still, let's see, what's today? The 10th? 1, 2, 3, 4, 5, 6, 7, 8. We still have 8 more classes.
4 weeks.
Right?
It's not before the final?
I'm sorry?
It's not before the final?
And then we have the final after that. So we have 8 class meetings, and that's a lot of material still. So just try not to get too complacent, or else you're just going to get rolled over by chapter 8. All right? All right, so I handed out something to you today. This is a really nice summary of a lot of the things that we're going to be doing in the next few sections. And for those of you who are going to go on and do some more math or engineering or anything that series might pop up again, this is a good reference page to keep handy. Because it brings together all the different techniques that we have for attacking a series and trying to figure out whether or not it converges or diverges. So what I'll start with today is what we ended class with last time, and that's the first test that is on this sheet. So the way this is laid out, it gives you the name of the test, the nth term test, and then, what is it used for? Well, it's used when you're looking at some series like this. What does the test say? Well, it says that if the limit as n goes to infinity of a sub n does not equal 0, then what happens? The series diverges. And then there's a comment section on the side that says, if the limit as n goes to infinity of the sequence is 0, what? It's an inconclusive test, which means you don't know anything about what happens. So what makes this nth term test nice is that all it involves is looking at the sequence, right? That's all you have to look at is the sequence itself. You don't have to look at them, each one added up, or the whole thing added up forever. You're just focusing all your attention on just the sequence and taking that limit. If it turns out to be something other than 0, you're in business. So let me give you a quick example of something like this. How about find whether or not this converges or diverges. Sum n equals 1 to infinity of 4n squared plus 1 over 3n squared plus 4. So is this anything that we talked about last class? Because we did talk about 2 types of series last class. Do you all remember what they were? Geometric and harmonic, right? Those were the 2. And these actually appear, let's see, harmonic is not on here, is it? No, hold on. Actually, it is. It's the P series, but we need to talk about that still. But geometric series is on here, isn't it? And this whole summary of how the geometric series works is here. So is this a geometric series? What do we look for geometric? What do we want the n to be in the exponent, don't we? And it's not happening. So this is not geometric. Is it harmonic? So what did we look for harmonic? Constant over a linear expression, right? That's what we're looking for. This is not a constant over a linear expression, so this is not harmonic. So if it's not the 2 things we've looked at, then it's got to be something else, right? So we're going to try this nth term test first. Let's take the sequence here, a sub n, and let's apply the nth term test to it. So I'm going to do, so watch, I'm going to write this out the way that I would do it if I were doing this problem. I would say to whoever's looking at my work, I would say here, nth term test. All right? I'm going to write that out so that everyone knows that's what I'm about to apply. And that means I'm going to take the limit as n goes to infinity of 4n squared plus 1 over 3n squared plus 4. And we know that that's infinity over infinity. So we can apply L'Hopital's rule, right? Now we're supposed to switch n over to x and make it real values, right? But we get to a point where we all, I'm sorry, I'm kind of congested, where we all understand that we can go to L'Hopital, switch it to x, and then switch back, right? So without loss of generality, that's what we like to say sometimes, we are just going to apply L'Hopital's rule to that. So we're kind of breaking the law here a little bit. But I think we could all agree that we could easily get to x and then back. So we would get what, 8n over 6n? Agreed? The n's would cancel, and you no longer have a problem, right? This is just 4/3. So that number is not 0. And because it's not 0, the nth term test tells us what? The series diverges, right? So I'm going to state here, since this is not 0, my conclusion, I'm going to very, very explicitly tell you what the conclusion is. Therefore, the series diverges, and I'm done. So the work that I would look for on a problem like this, on a test, would be that you clearly state what test it is you're doing, and clearly show, this is where you're showing, right here, is where you're showing that your test actually gave you a result that you can work with, right? This is showing you divergence right there. And then state your conclusion. Make sense? The nth term test is something that you want to do every time you have a series that you can't tell right away what's happening. All right, it's kind of like the first test. In fact, I did all the homework for 8.3 this morning. So we're not even in 8.3 yet, but I was doing all the homework for 8.3, and I got to a problem. I was having some trouble with it, and it was the nth term test. It was the first thing I should have done. I even got used to just trying something else that I forgot about this test. So, yes? Always remember it's here? Okay. All right. So we'll use that when we can. Now, we're going to move on to another type of series now. So let's go now and talk about what's called a telescopic or sometimes referred to as a collapsing series. Now, I'll tell you where the name comes from after we do one, all right? Because it'll make more sense after I actually do the problem. So take a look at this series. I want to know if this converges or diverges. So I'm going to put C/D for this problem. Is that all right for everyone? So I don't have to write converge or diverge. So converge or diverge. Sum n equals 1 to infinity of 1 over n plus 3 minus 1 over n. So what do you think? When you look at that, is there anything that you notice or see or What do you see? You see harmonic, don't you? Everyone see that we have a constant over linear? And then constant over linear again? And we know that a constant over a linear, that's divergent, right? It's harmonic. Here's the problem, though. We're subtracting these two, right? And so you might think, okay, sure, I should be able to, don't write this down. You might think, oh, okay, I can just split this into two, like that, and say, oh, well, that diverges, and therefore it all diverges. Or they both diverge, so the whole thing diverges, right? That's what you might be thinking. But you can't. And there's the properties of sums are on page 441. I'm not going to write them out on the board because it takes too long. But one of the properties says is that the only time you can take a sum like this and split it into two, the only time you can do that is if they both converge. So if this converges and this converges, then you are allowed to do it. But if either one of them diverge, you cannot split it. You have to leave it like this. Understand? Yes or no? Yes? Okay. So we're stuck, right? That's not going to work. So now, since we're kind of stuck, let's take a look at, let's just write some of these things out, right? How about we do that? Like, what is this? This is plug in 1. What do we get? So 1 over 1 plus 3 is 4. So we get 1/4 minus 1, and then plus, now we move on to 2, right? Plug in 2, we get what? 1/5 minus 1/2 plus what? Keep going. 1/6 minus 1/3 plus 1/7 minus 1/4, right? Plus, I keep going, right? When do I actually stop? I never actually stop, right? It keeps going forever. Does anybody see something in there? What cancels out? This 1/4 here and this 1/4 would cancel, wouldn't they? They're opposite in sign, 1/4 and then minus 1/4. You'll see that? And then this 1/5 cancels out with this negative 1/5 here. How about this 1/6? I would have to go more further out, but it's out here, isn't it? And a 1/7, it's out there somewhere. And the 1/8 is out there somewhere. Do y'all kind of see things are starting to cancel out? All right? So here's what we're going to do. We're noticing some cancellation in there. That's the key. It's the first thing you need to recognize a collapsing series. You have to see some cancellation happening. Then we're going to go back to, look in your notes, the definition of what we meant for a series to converge. So go back to your notes. In your notes, it said something like, we say a series converges if S sub n goes to L. See, if you go back in your notes, you'll see this somewhere. If S sub n goes to L. And this S sub n right here was what we called the nth partial sum. So maybe it'll ring a bell if I say it this way. If I just go out on this sum, right, this goes from 1 to infinity. If I just say, look, just take the first one and add them up, you get an answer, right? Yes? If I say now just go from 1 to 2, you would take the first 2 and add those up and get an answer. If you take the first 3, you get those together and you get an answer, right? We said that those answers created a sequence. And that sequence that we created was what we called S1, S2, S3. It was a sequence of sums. And what we're looking for is for the sequence of sums to go to a number. And so that's what we meant by this. All right? Okay, just follow along right now and see if you can handle this. What I'm going to do is this. I'm going to figure out what the nth partial sum is of this. And then I'm going to let n go to infinity. When I do that, I'll be trying to figure out if it goes somewhere. I need a little more room, so let's see what I can do. Let me rewrite the series up here, so that way I can refer back to it. Here was the series. And we already know that we get cancellation, right? Yeah? So now I'm going to write down what S sub n is. S sub n is what I get when I start adding these up and stop at n. All right, when I stop at n. So we already said the first thing I would get was 1/4. Notice I'm writing very small because I'm going to go pretty far, okay? I'm going to go 1/4 minus 1 plus the next one was 1/5 minus 1/2 plus the next one was 1/6 minus 1/3 and then plus 1/7 minus 1/4. Do one more, plus 1/8 minus 1/5 plus, right? Dot, 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 dot means it keeps going, right? But I'm going to stop it. And I'm going to stop it where? At n. So what's the last one over here look like? 1 over n plus 3, and then minus 1 over n. Agreed? So this is what happens if I stop at n, right? Stopping at n. What does the one before this look like? It's what I get when I take, instead of plugging n in, I plug in what? n minus 1, 1 less than it? So what would happen if I go to this expression, I replace this n and this n with n minus 1 instead? 1 over n plus 2 minus 1 over n minus 1, right? And I'm going to keep going back until I see cancellation. So you notice over here, when I did this, I noticed that I had the cancellation with the 1/4 there. I actually don't want to write over those yet. But do you see I had a 1/4 here and a negative 1/4 here? I had a 1/5 here and a negative 1/5 here. So I know I'm getting some cancellation. Yes? I want to come from the back side this way and see where that cancellation occurs. So do I have cancellation yet? Like, do any of these cancel? None of these are identical, are they? So I need to go back another one. So this time I'm going to be plugging in, what? n minus 2. What happens when I plug in n minus 2? 1 over n plus 1 minus 1 over n minus 2. Do I have any cancellation here yet? Any of these the same? These aren't the same, though. No. Right? So let me go back one more. I think I'm going to get it on this one. What am I plugging in this time? 1 over n and minus 1 over n, what? Minus 3. And I hope that comes out on camera okay. Can you all see it? You sure? Everyone understand there's dot, dot, dots in between here? I just am out of room? Yes? All right, so now what we're going to do is we're going to try and pick up on the pattern of cancellation that we have. Pay attention to the way I say this, okay? I want you to notice that the first number in the first parenthesis is killed off by the second number in the parenthesis, how many away? 1, 2, I'll say 3 away, right? So, or you could say 1, 2, 3. In the fourth parenthesis, right, the second guy is killed off by the first guy over here, right? Now, I'm going to stick to the way I like to say it. The first guy in the first parenthesis is killed off by the second guy in the parenthesis 3 away. Let's see if that pattern holds again. Is the first guy in this parenthesis killed off by the second guy 3 away? So if I go 3 parentheses away, 1, 2, 3, the second one should kill that one off, right? So first, guys, are killed off by second guys, but I've got to go 3 to the right, yes? So this first guy, is he going to be killed off? Yes, because there is something in that dot, 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 right, that will kill him off. The next first guy is 1/7. Is he killed off? Yes, because there's something in that dot, dot, dot 3 away that will kill him off, yeah? How about the 1/8? Same thing. That somewhere in there, it's going to start to look like a cluster, you know what I'm saying? It's going to be a mess. But all of those things circled are gone, aren't they? All right, let's talk about the second guys, because I haven't talked about the -1, the -1/2, the -1/3. I haven't talked about that yet, have I? But they are second guys, aren't they? Second guys are killed off by first guys, aren't they? But, what, 3 ahead, right? So this -1, for it to get killed off, I would need to have something before it, which I don't have, do I? So he stays. I'm going to put arrows on everything that stays. That guy's still there. This guy right here, does he get killed off? No, because there's not something 3 away. So he's still there. On the next problem, there'll be she's, right? Just to keep it cool in here, all right? This problem, these are all he's, all right? This stays, right? There's nothing 3 ahead. But from here on, they were gone, aren't they? All the second ones are gone? All right, let's talk about the tail end of this sum. First guys get killed off by second guys 3 away. So this guy should get killed off if there's something 3 away. 1, 2, 3. There it is, right? So this guy right here gets killed off by this right here. They're gone. All right. How about this first guy? Doesn't go anywhere. Because you would need something 2 away, right? And I stopped at n. Right? I stopped at n. So there is nothing to kill off this one 3 down. So that stays. Let's get these arrows out of here. Those are confusing now. How about this first guy? Nothing down there, stays. This first guy? Nothing down there, stays. What about the second guy here? The second guy has to be killed off by something 3 in front. Do I have something 3 in front of this one? Somewhere in there, right? Somewhere in the dot, dot, dot. This one gets killed off. Somewhere in here. This second guy, same thing. This guy gets killed off by something in there. This one right here, killed off by something in there. And the last one, well, we already took care of the last one, didn't we? So the arrows, those arrows, are all that remains, right? It's all that remains. So would you say that we have some stuff in the front that stayed and some stuff in the back that stayed, but everything in the middle canceled? What were these called? What types of series? Collapsing. Imagine a bridge going across, and you imagine the bridge collapsing, right? Everything in the middle falls out. You got the ends still standing. That's kind of the idea. The series collapses in the middle, and you're just left with stuff at the ends. Telescopic, old school telescopes, you know what I'm talking about? You look through it, you collapse it down, right? And you wind up with the 2 ends coming together. That's the idea behind the language of this. So S sub n is equal to whatever was left. 1/4 plus 1/5. No, shit, those were gone, sorry. -1 minus 1/2 minus 1/3, those 3. And then down here, -1 over n minus 2 minus, Jesus, Robert. No. What's happened is, what I'm used to doing when I do these is I actually cancel these out so I don't mess them up. Like I actually come in here and cancel them like that. I was using circles so you could still see the numbers and not get too crazy, but this is a little easier for me to see what's left. This one's left, right? And then this one's left. And finally, this one. So this is a sequence, isn't it? This is a sequence. S sub n. What's that?
Series?
No, this is a sequence of numbers, isn't it? If I plug in 1, I get an answer. If I plug in 2, I get an answer. If I plug in 3, I get an answer. The question, and each of those answers represents me going further out in this sum, right? As I make n bigger, it pushes this side out, doesn't it? Makes this sum longer. And what I want to know is what happens as n goes to infinity now. So all you have to do is take the limit of this as n goes to infinity, and that's the answer. So what is the limit as n goes to infinity of S sub n? So look at this right here and tell me what happens as n goes to infinity. It's just the first three numbers. -1, -1/2, -1/3. Right? Because this goes to 0, this goes to 0, this goes to 0. And let's figure out what that is. Get a common denominator. How about 6? So -6/6 minus 3/6 minus 2/6, which is -11/6? -11/6.
So the answer is going to be the series that converges to.
That's right. This is what the series converges to. If you were to go out and start adding these things up, right? If you were to do 1/4 minus 1, 1/5 minus 1/2, 1/6 minus 1/3, and you were to go forever, if you could go forever, if you could, you would get closer and closer and closer to -11/6. That's what it converges to. But the setup of the problem is the most important thing. You first recognize you have cancellation from the very beginning. Then you write out S sub n. And this is the part that everyone messes up on the test. They don't do S sub n. They do take a limit, but they don't write it down properly, and I take off for that. You have to write down S sub n and write down what that partial sum is. Then, once you figure out what the partial sum is with the cancellation, then you take the limit and you get an answer. I'm going to do one more of these, all right? The setup's going to be exactly the same. We're going to look at the series. We're going to try and find cancellation. We're going to write the partial sum. We're going to figure out what happens with the collapsing. We're going to take the limit, and that'll be our answer. All right? What does a harmonic series do? Diverges. Geometric series converges if the absolute value of r is less than 1. Diverges if the absolute value of r is greater than or equal to 1, right? So you're telling me that if I give you a geometric series with the absolute value of r less than 1, you can tell me what it adds up to be, right? It's a over 1 minus r. There's a formula for the answer. So a geometric series is a series we can actually find the sum of, right? A telescopic is another type that you can find the sum of. Like we can actually find what the number is if it converges. The reason why I'm bringing this up is because on a test, I like to give problems where I say find the sum. Okay? I say find the sum of this series. That's different than asking if it converges or diverges, right? I'm telling you there is a sum. And that, to you, should set off a little alarm that says, wait, he's telling me to find the sum, which means that it must add up to something, which means it's got to be geometric or telescopic. It narrows everything down for you. That kind of makes sense or not? Okay. Let's do another one.
Never diverges.
What's that?
This one never
You
diverges.
can have this diverge. Just like geometric series, it can. But if you're ever asked to find a sum in this class, it's either going to be geometric or telescopic. It's going to be one or the other. Let me see here. Sum n equals 2 to infinity of negative 3 over n squared minus 1. Instructions here, find the sum. So I'm hinting to you that it does add up to be something. In your homework, when you get to these problems, it says here, these are problems number 25, 26, 27, 28. It says, determine if the series is convergent or divergent by expressing it as a telescopic sum. So they're telling you within the homework problem that it's a telescopic series. I won't do that on a test. I'll just tell you, like, find sum. And then you kind of have to know what that means. What's that? Okay. So what now? N plus 1. So you want to do the nth term test just to start to make sure this doesn't, like, it's not easy? You want to do that real quick? Nth term? What's the limit as n goes to infinity of negative 3 over n squared minus 1? It's 0. What does that tell us? It doesn't tell me anything. So that failed. But that's okay. At least I know it wasn't easy right off the bat, right? All right. So is it geometric? No, because n's not in the exponent. Is it harmonic? It's a constant over a quadratic. That's not a harmonic, right? So maybe what you would do next is you would say, all right, let me write out some of these to see if I can get some cancellation, right? That's what you might think. So let's just see what happens if I start plugging things in here. What if I plug in 1? Notice I'm starting at 2. Why am I starting at 2, not 1? Because 1 would give me division by 0. So I started it at 2. No big deal. So 2, if I plug in 2, I get negative 3 over 3. So it would be negative 1 plus, what's the next one? Negative 3 over 8 plus negative 3 over 15 plus negative 3 over 24 plus ... Right? Can anybody tell me why you should be concerned? Nothing's canceling, right? I mean, do y'all see that? Nothing is canceling here? I mean, we would, at the minimum, we would need at least some of these to be positive, wouldn't we? They're all negative. So your instinct here would be like, well then, I don't know, maybe it's not telescopic, right? Right? I mean, it kind of looks like, how could it possibly be telescopic? So I heard something to factor the denominator, because it's a difference of squares. We could do this, right? We could do that. And if we start plugging numbers in now, it's not going to change anything. We're still going to get this same result. Nothing is going to cancel. But what's that mean? What do we call that? Splitting it. I don't know. We did. There was an entire section on this with integration. It was the last section of integration.
Divided as two different fractions?
Yes, we call that
Oh my God, no.
partial fractions. Partial fractions. We should be able to split this up into two different pieces. So I'm going to stop for a second. I'm going to do a real quick partial fractions here. Did you just say ridiculous? Oh. Oh. I thought you said this is ridiculous. So the way we did this, we said we had two distinct linear factors, right? Distinct linear factors. So I put a over n plus 1 and then b over n minus 1, right? Something like that. And then I figure out what a and b are, right? So I have to do my little thing. We've done this a lot, I hope. Then you could say, hey, look, let's kill off b. Let's let n be -1. And then when you do that, I thought I made this where it was going to work out nice. Oh, shit. Okay, if n is -1, what do we get? -3 equals a times what? -2. Sorry, I was trying to avoid fractions. I must have messed something up when I was putting the problem together. 3/2 is a? That's a. All right, what's b? So let n be what? Let n be 2? No, let n be 1, right? That's going to give you -3 equals 2b. So -3/2 is b. Is that okay? We all right with that? All right. So here's the way I can rewrite this series. I'm going to come back up here and rewrite it. It's going to be rewritten as, in parentheses, a over n plus 1. So 3/2 over n plus 1 plus b, which is -3/2 over n minus 1. Y'all still there? Everyone still there? Got it? And I can start working with that right there. Now I'm going to change it a little bit because I noticed that both numerators have 3/2. And I'm going to factor 3/2 out, and I'm going to pull it out of the sum. So I'm actually going to have this. 3/2 comes out of the sum. N equals 2 to infinity. And then what's left in here is 1 over n plus 1 minus 1 over n minus 1. And so what I did when I pulled the 3/2 out of this, I was left with a -1 there. And I just changed that to a minus and made that a positive 1. Do y'all have any questions? Sure? Let's write out what this would be equal to. 3/2 out in front, right? And then here's our sum. Let's plug 1 in first. What do we get? We plug in 1. 1/2, sorry, you plug in 2. Thank you. We were about to have division by 0, weren't we? Plug in 2, we get 1/3, right, minus 1. Now plug in 3, we get 1/4 minus 1/2. Keep going. 1/5 minus 1/3. Oh, you see it? There's going to be a canceling right there. And then 1/6 plus minus 1/4. There's another canceling, isn't it? Yes? And that keeps going forever. So I've recognized I'm going to get cancellation. And since I've recognized that I'm going to get cancellation, I now need to do what? S sub n. We need to figure out what S sub n is. What is the partial sum? So I'll write it down. So notice that what I'm doing here is I'm kind of stopping. I'm saying, okay, I've got a pattern. I've got it to get canceling terms. So I need to figure out what the partial sum is. The partial sum will be equal to 3/2. So I'm carrying that with me. And then let's write out this partial sum. This is where I'm going to have to write real small. The first piece of the partial sum is this. So I'm just going to repeat this, right? The only difference is I'm going to have to add a tail piece onto this. So 1/3 minus 1 plus 1/4 minus 1/2 plus 1/5 minus 1/3 plus 1/6 minus 1/4 plus, I think that'll be enough. I get 2 cancellations in there, don't I? I have 2 of them right there. So that should be enough for me to pick up the pattern, hopefully. And then plus, let's get the tail piece. So I have a bracket down here. I already know I'm going to probably have to have 3 of these to see the pattern. Yeah, it's good enough. What's the last one? Plug in n, so you get 1 over n plus 1 minus 1 over n minus 1, right? The one before that is going to be just take 1 away from each of these. So 1 over n minus, what? 1 over n minus 2. The one before that, 1 over n minus 1 minus 1 over n minus 3. Do you want to go one more? I have space for it. I have space. You're out. 1 over n minus 2 minus 1 over n minus 4. Now look, the pattern in this one I think is exactly the same as the last one, but it's not always that pattern. All right? You might have, if you get lucky, you might have the first one here canceling with the second one here. They might be right next to each other. They might be 2 down, might be 3 down. I'm not going to go past 4 down. Okay, I won't be that mean to you.
You can kind of tell how far down you have to go by
The-
the plus 1 and minus 1.
That's right, the distance between those 2 numbers. Yep. Oh yeah, it's not 3 down in this one, right? It's only 2 down. So let's start canceling. And this time I'm not going to circle. I'm going to just cancel them because it confused me last time. This 1/3 cancels with this one right here. So the first girl cancels with the second girl 2 down, right? See, it works better with guy?
Yeah.
Okay, we'll do guy then. If there are no objections. All right. All right, so look, here we go. First guy cancels with second guy 2 down. First guy going to cancel? Yeah, because there's going to be a second guy 2 down somewhere in there. First guy here? Gone? Somewhere in there. Second guys require something in front, so this second guy stays. I'm actually going to circle the ones I want to keep this time. Sorry if that confused you. Those 2 stay, don't they? Now, back here, first guy cancels with second guy 2 down. First guy, does this first guy cancel? First guy cancels with second guy 2 down. This first guy? Stays, right? He does not have anything 2 down. This first guy? Stays. How about the second guys here? Second guy requires first guy 2 in front, somewhere in there. Second guy requires first guy 2 in front, somewhere in there. This one's gone. Okay, so I think I've got everything, right? It has collapsed on me. So S sub n is equal to whatever's left. -1 minus 1/2 plus 1 over n plus 1 over n plus 1. Let n go to infinity now, right? It's -3/2. Yeah. So now we take the limit as n goes to infinity of S sub n, which equals -1 minus 1/2, which is -3/2. This converges. The series converges to this. All right? Is there a problem? Y'all are all looking at me like I'm crazy. Why what? Oh, the 3 halves in front. That's what you're talking about. Yeah, I forgot about it. So this,
You just gotta put a square on.
look, this right here, I'm glad y'all said something because it would have been wrong. I need 3 halves in front of that, right? This 3 halves right there. And then that puts some 3 halves here. I'm going to tack it onto the back of this, which means, what's our answer? We're multiplying, right? Right? Negative 9/4. Sorry about that. What's wrong, everyone? Only if there's a number that goes into both of those. You're trying to take square root of both, maybe? No? What do y'all think? Telescopic. Kind of weird, huh? So I'm going to give you a hint on a problem like this. If someone were to give you natural log of n over n plus 1. Try nth term first. If you do nth term, you get infinity over infinity here. You could do L'Hopital on that, and that would give you a 1. And natural log of 1 is 0. So the nth term would tell you nothing. So you'd start to try and figure out what's going on. It's not geometric. It's not harmonic. How could that possibly be collapsing? That's right. You can split it into 2 logs, can't you? I don't know if that's what you were going to say, but if you have log of division, you can split it into 2 logs with subtraction, can't you? And now you could start writing each of those out, and you would start to get collapsing at some point. And I can almost guarantee you on that one will diverge. Because when you get to the very end, you're going to have some stuff stuck at the end, some stuff at the beginning. The stuff at the end is going to have natural log of n in it. And when you let n go to infinity, natural log of infinity goes to infinity. So that's going to diverge. But there's one like that in your homework. Actually, that one is in your homework. It's number 26. So I did that, I'm sure, on the video. All right. That's it for telescopic, okay? So we're starting to get a bucket of series that we can deal with now. We've got geometric, harmonic, telescopic, right? Geometric, harmonic, and telescopic. The next type of series that we're going to discuss are what are called P-series. And this is on your sheet. All P-series look like this. The P stands for power, okay? And so what you notice is that with the P-series, the n is not in the exponent, so it's not geometric, right? It's not a geometric series. You have 1 over n to a power. And this series might converge, it might diverge. It depends on P, and that's all it depends on. And I'm not going to go through the proof of why this is true just because of time restrictions. But I think you'll agree with me. We already know what happens if P is 1, right? If P is 1, this is harmonic? Yes? So I know that P is 1, it's going to diverge. Well, it turns out that if P is less than or equal to 1, it will diverge. And it turns out if P is greater than 1, it converges. And we're just going to accept that and be okay with it and move on with our lives. This is on your sheet, okay? It's on here. But I'm just stating it up here so we see it. So let's take a quick look at an example of a P-series. Here we go. Some examples here. Converge or diverge? Question. Sum n equals 1 to infinity of 1 over n squared root n. So you start running through your table of ideas. Is it geometric? Is it harmonic? No. Is it telescopic? Probably not, because if it was telescopic, I would have to be able to break it into two pieces, right? So I could get some subtraction in there. Doesn't look like it's telescopic. Oh, nth term test. What would happen if we did nth term test? That would go to 0, which doesn't tell us anything. So really, we're kind of running out of options here. So is it a p-series? I could rewrite that as 1 over n to what power? It's n squared times n to the half, isn't it? That's what that means? So you add the exponents, 2 plus a half, 5 halves. This is n to the 5 halves. And that is a p-series, isn't it? P-series with p being? P is 5 halves, which is greater than 1, isn't it? So the power is greater than 1, and therefore what? It converges. Therefore, it converges. Right? We don't know.
Would that answer suffice?
Because I'm asking if you converge or diverge. If that's what I'm asking, that's all you have to answer. And like I said in the very beginning of this, for where we're headed, convergence or divergence is all we really want. Okay? We don't care what it goes to. If there's anyone who is having some trouble with their grade at the end of the semester, I'm going to offer, it's going to be about a 1.5 hour lecture over Fourier transforms. And if you come and you attend that, you get bonus in the class for attending the lecture. And I will show you how difficult it is to get some of these series to actually find their sums. But that there are ways to do it. But they're just really complicated. Probably after the final. Yeah. I'll let you know later. Yeah. On campus somewhere. Yeah. No. Yeah, we're just going to, yeah. I'll let my wife know my Cal 2 class is coming over. Just making sure there's nothing else. Oh, how about this? I have a question for you here as another example. Sum n equals 900 to infinity of 1 over, well, let's make it negative 11 over n cubed. What do you think? Think it's a convergent p-series? Yeah? Does the fact that it's negative 11 up there bother you at all? Okay. Because you could probably just take that negative 11 out, right? Right. Is that okay if I do that? Yeah? And this is a p-series? P being 3, which is bigger than 1, so it should converge. So if this converges to a number that I multiply by negative 11, it's still a number, right? But there's something else. It's not bothering anyone? The sum is starting at 900. Do you think that that's going to matter? No. What does the formula say? It says p-series looks like this. N equals 1 to infinity of 1 over n to the p, right?
It needs to be starting at 1?
That's what I'm asking you. What do you think? Does it need to start at 1 for me to be able to say converge?
It gets to 900 at some point.
This right here, right? This right here is actually the sum n equals 1 to what? 899 of 1 over n to the p plus sum n equals 900 to infinity of 1 over n to the p. Would you agree with that? And if I know that this adds up, converges to a number, and it's equal to these two sums, then these two have to be finite numbers, right? There's only one way I can add a number to a number and get a number is if they're both numbers, right? Like whatever this number is. So it's like what you're doing, this piece right here, right, is just that piece. So it's actually smaller than the whole sum would be, wouldn't it be? So it's got to still converge. Does it work with divergence? What do you think about that? So let me change the problem. Let me make it this. Negative 11 over n. Does that change your answer? Or are you still going to say diverge? Still diverge? This is a more profound question. Converge? Let me see if there's a way I can show this graphically to see if it makes sense with a picture. I'm going to draw two situations. Let me tell you that if I take this bucket, I guess, and I stack up 1 through the infinity layers of, I'm pouring stuff in here, and I'm going to have 1 layer, 2 layer, 3 layers, and I'm telling you that if I put an infinite number of layers in here, it converges to a number, right? Then if I just stack up, if I ask you to just look at 900 and up, that has to be a number also, right? It still has to converge. If the whole thing is a number, then just part of it should also be a number, yeah? But what if I tell you this? I have bucket, and I stack in this layer of something, and when I stack the layers, it actually overfills the bucket, right? It's going to overfill. So this diverges. Understand? Then if I ask you to look only from 900 outward, can you say that that has to diverge? What can you tell me about this? This is a number, right? This is finite, which means the rest of it has to be infinite, right? So there's a theorem in the book that says, or there's a property that says that a finite number of terms of a sequence has no effect on its convergence or divergence. So if I take out the first 899 pieces, it has no impact on whether or not it converges or diverges. What I can't do is take off the tail end that goes to infinity. Now that would change things. So this would still diverge, which means the whole thing diverges. All right? All right, that's more of just an FYI. I don't think that comes up in the homework. All right, we doing all right? We've got 40 minutes still. I'm just making sure. I think I'm done with 8.2. Yep, that's 8.2. That material up to that point will guarantee be on your test on Tuesday. Right?
The test has to be on Tuesday?
Pardon me?
The test has to be on Tuesday?
You want to move it to this Thursday again?
Next Thursday?
Next Thursday? Then you're going to have all of 8.3 on it. Let's see how today goes, like the rest of today and maybe tomorrow. I mean Thursday. My plan is to do the test on Tuesday.
Are you going to give a bonus? Like the problems, like we do them and then they come in?
I hadn't thought about it. I'm not sure. Hadn't really even considered it.
I got so many points on that. 0.5.
Really?
All right, so if you look down our handout, the nth term test we've got, the geometric series, we kind of know what those look like. We just talked about p-series. The next two things on our sheet are the integral and comparison tests. So I'm going to go through the integral test first, and then I don't know if I'll have time for comparison test. So let's see if we can first read what the heck this says. The integral test says that you're trying to look at a sum, n equals 1 to infinity, a sub n. So you're trying to look at this series, right? This is integral is what I'm doing right now, integral test. You're looking at this series, you're having trouble figuring out what it's doing, all right? It doesn't fall into any of the categories that we've looked at so far. So you're like, all right, what do I do with this? Well, you transform the sequence into a function. And I'm going to say a function of x because that's the way I do the entire homework set on video. So I'm transforming my sequence, which is a bunch of dots, over to a function, which is a function of all real numbers. We've done this before, haven't we? Okay. This test says we have to have some conditions. If, and this is, I'm looking at the far right side of the table, on the comments, if f is continuous on 1 infinity and f is positive on 1 infinity and f is decreasing on 1 infinity. I'm going to add something to this. We actually don't need that strong of a condition. Do y'all remember what it means for a function to be decreasing? It's going down from left to right? Okay. We actually don't need it to be decreasing on the entire interval. It really can just be, instead of this, what I will say eventually. So it can the function that we come up with from the sequence can go up and down a little bit, but eventually it needs to go down and keep going down, right? And stay going down the rest of the way. Okay? And the last thing, I don't want that in red. And f is integrable. What does that mean? You can integrate it. Integrable. Weird word, huh? So summary, I haven't said what the test says yet. I've just shown the conditions for the test. You have to be looking at a sequence, you have to basically be stuck on it, and then you have to say, wait a minute, hold on. If I turn that sequence into a function, like from, just a function of normal variable x, then as long as that function is continuous, I can draw it without picking up my pencil. As long as it's positive, always above the x-axis. As long as it's eventually decreasing, and as long as I can integrate that function, then here's the result of this. What is the result? Then, I'll put it up here. Then, if the integral of the function on the interval 1 to infinity converges, so does your series. On the other hand, what do we mean by the integral converging? It's going to give it a finite number. If my integral, when I do my integral, if it turns out to be a finite number, what that tells me is that my series had to do the same thing. And then the other result is, if the integral diverges, guess what? So does my series. This is an awesome test. It just kind of sucks to apply it, okay? It's not fun to apply this test, but it's powerful. and every Cal 2 student should know how to apply the integral test. So let me see if I can convince you quickly as to why this works. All right? Remember that when we have a sequence, it's just a bunch of dots, right? And when we add them up, we get the series. Right? That's what a series is just adding up a bunch of numbers. So imagine I have a sequence that is eventually decreasing. Right? Like this. And notice I'm staying above the x-axis. Why am I staying above the x-axis? Because I have to stay positive also, right? So I have a function, I've got a sequence that's decreasing. If I, instead of looking at the sequence of dots, use a function instead, right? That's f of x. I have a continuous, nice, smooth curve. It is positive above the x-axis and it is decreasing. Then what does this integral represent? Geometrically, what does that integral represent? The area underneath that red curve, doesn't it? It means starting at 1, find that area, right? If that area is finite, then the sequence has to be finite. Or the series does, because isn't the series just adding the heights of each of these lines? Isn't that right? I take whatever the first number is, I stack this one on top, that one on top. So you're just adding up all these lines, these lengths. Those lengths have to be less than the area, doesn't it? So if the integral converges, so does the series, right? On the other hand, if this area is infinite, the series has to be infinite. That's not as easy to show. And I can't prove it in here. Okay, it's not part of this class to prove why this second one is true. This one might be hard for you to convince yourself of. If this area is infinite, does that mean that the black lines have to be infinite? Well, it turns out that we've proven it does. Okay, so we won't argue about that. This one's easy to show, I think, geometrically. This one's a little harder. All right, you want to see this in action? Of course you do. Here we go. Let's take the series converge or diverge. Sum n equals 1 to infinity. Yeah. Natural log n over n. What should we start with? What's that? Nth term? You want to just try real quick? Nth term test? Okay, nth term. Nth term, limit, n goes to infinity. What am I hoping for here? It's not 0, right? That's what I'm hoping for. So right now I'm infinity over infinity. One application of L'Hopital's rule. 1 over n over derivative natural log 1 over n over 1. Where does that go? 0. Fail. Cross it out, whatever. Right? So that didn't work. Okay, is it geometric?
No.
N's not in the exponent. Is it harmonic?
No.
It's not a constant over linear. Is it a telescopic? Is there a way you could split it up so that you could get subtraction in there? No, because that natural log, you can't split it into two logs because you would have to have division inside of the log. This is division log separated from something else, right? What else do we have? Is that a p-series? Well, it's n to the first power, but the top would have to be like a number, like 1. So it's not p-series. So it's nothing we've seen, right? So what you would want to look for before you start thinking integral test is you would like to look at the inside, look at the sequence in here, write it as a function of x. And before you even start this, ask yourself if you would ever want to integrate that. Because if you don't want to integrate it, I wouldn't try the integral test. Could you integrate that?
Yes.
Yes? That's a basic u sub, right? If u is what?
Something in this week.
Something as derivative. So do you see the something? Natural log x, what's its derivative? 1 over x, it's there, right? So you can integrate that? Okay, so maybe the integral test. So I'm thinking integral test right now. So I'm going to write it down. Integral test. I'm letting everyone know what I'm about to do. This part of what I'm doing is really important, all right? When I do the homework videos, if you watch those, I try, at least for the first 20 or so problems, I'm very meticulous about the way I write things because that's what I expect for you to do on a test. You need to show me each test because all I'm asking is convergence or divergence, right? If you just have a bunch of chicken scratch everywhere and it's just like your random thoughts all over the page and at the end you get divergence, but I can't tell what in the hell you did, but you're right, I can't give you full credit. I have to be able to follow your logic. And so I need to see, okay, you tried nth term test, it didn't work, you stated that, you moved on to integral test. I see you showing all the things you need to do integral test, doing your integral properly, and drawing your conclusion. If you get an incorrect conclusion but you show all your work, you get partial credit for that, all right? Because at least you're going through a procedure, a process. All right, so what do we need for the integral test? We have to have conditions met before we can do it.
Positive.
Okay, you have to show all of this. If right now you just set up an integral, if you do this and you get your answer, you're going to get like, if this were 10 points, you would get 2 points. You have to show me you can use the integral test before you use it. You ready? So what's the first thing I need to show? F continuous on 1 infinity. This is the question. Is it? Why? Natural log is continuous. X is continuous on 1 infinity, right? Because at 0, they're both in trouble, right? But I'm not looking at 0. So is this? Yes. Ratio of 2 continuous functions. This part of chapter 8 is really where I start to notice the differences in students and just how well people can organize their thoughts and put them on paper. Because as an engineer, or whatever it is you're going on to do, whether it be biology or whatever, getting the information from here to on a piece of paper where you can hand it to a colleague and they can go, okay, got it, I understand what you're talking about. That is a skill. That is something that you acquire. All right, so what you want to be thinking about when you write this is, are you communicating what you're doing to whoever is reading this? I think I have, right? Yes? All right. What's next? F must be positive on the interval. Question, is that true? It is? Okay, so let me show you why it's positive. I need to show you that natural log of x over x is greater than 0, right? That's what I need to show you? Right? Is that true? Is natural log of x always positive? Not always, right? What does natural log of x look like? Looks like this, doesn't it? Isn't it negative sometimes? But where does it switch?
1.
At 1, right? And where am I looking? 1 to infinity, right? So at 1, isn't this 0? Yes? But after 1, what is it? The top's positive, and of course the bottom is going to be positive because x is positive. So there's only one place where it's not positive, right? So this condition of being positive on the interval, do you think I violated it by being not positive at one point? It turns out it's okay as long as after that it's positive. So we are still okay with this, all right? So this is checked because natural log of x is greater than or equal to 0 on 1 infinity. That's that. And of course, x is greater than 0 on 1 infinity. So if I take a positive number and divide it by a positive number, I get a positive number. F decreasing on 1 infinity. But I said you don't have to show that much, do I? Do you? I said what? Eventually, right? Who wants to tell me how they would figure out if a function is decreasing? Anyone have any idea of how you could show me whether or not a function decreases? You could just look at, like, plug in values. That's a way of convincing yourself it's decreasing sometimes, but how do I show you it's decreasing on the entire interval? Think Cal 1. What was Cal 1 about? I'm doing this in my Cal 1 class right now. I did it yesterday. I did it. What do we have to look at to figure out if a function is increasing versus decreasing? The slope, right? The derivative. If the derivative is positive, the function is going up. If the derivative is negative, the function is going down, right? So all I need to do to show this is prove to you that the derivative is negative eventually. Do you agree? Is that enough for you? So I just need to show you right here that the derivative of f is negative. If I can do that, I hope you'll be convinced. Well, you better be, because that's what Cal 1 said happens. Okay, so that means we have to take the derivative of the function. What's the derivative of the function? Well, guess what you're going to have to do for that? Quotient rule. The quotient rule. Do you see why I said if you just do the integral right at the beginning of this problem, you're just going to get 2 out of 10 points? There's so much framework that has to be established before you can use the actual test that if you miss all this, you're missing like really the whole heart of the test itself. All right, so I'm going to take the derivative of the function itself, the derivative of that quotient rule, derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Agreed? And this is equal to, simplifying 1 over x times x is 1 minus natural log x over x squared. Now I need to convince you that this is negative. Eventually. What can you tell me about the denominator? If I'm plugging in numbers from here, right? These numbers down here are always positive. Actually, the fact that I square it doesn't matter, right? But do you agree that the denominator of this is always positive? Okay, what can you tell me about the numerator? It's negative what?
Negative x, so it's negative.
Well, 1 minus this, right? Is this going to be positive or negative? Is it always, though? Because what's natural log of 1? 0, so you get a positive, right? What's natural log of 2? Well, again, you go back and you look at the natural log function like this. At 2, it's somewhere, right? But eventually, right, this number will be bigger than 1. When I say that, I'm saying this number right here will be bigger than 1 eventually. And so we're going to eventually get negative. So the further you go out, the more you, well, I shouldn't say it that way. I should say that with this function, initially your derivative is positive, so it does go up, but eventually your derivative will switch to negative. It'll start coming down from this right here. Do you all see that or not? Yes? So I'm going to say that this is negative when 1 minus natural log of x, what? Is negative? Which means when the natural log of x, I just moved this over, as soon as the natural log of x gets bigger than 1, this is true. So eventually. All conditions are met? Continuous function? It's positive. It's decreasing eventually. It's integrable, because you told me in the very beginning you could integrate that. So since I've got all the conditions met, I can apply the test. Any questions? Here comes the test. The test is, I'm going to look at the integral from 1 to infinity of natural log x. Natural log x over x dx. Whatever this does, my series does. See, what will happen is someone will get a problem on a test, and they'll look at it and they'll be like, oh, I can integrate that. And they use the integral test, and they don't go through all those checks, and it turns out that one of those checks isn't true. And they get a conclusion that's completely wrong because the conditions weren't met. All right. So? First, I'll make it an indefinite integral. U sub. And that turns this integral into what? What is it? U du? U du? Antiderivative of u du? 1/2 u squared. But what's u here? Natural log of x. So natural log of x squared. That make sense? Yeah, I'm only saying that because it's been a while since we've done this, so hopefully the gears will start turning again for that. All right, now we go back here and we say, all right, we got to just do this now, right? But this was called an improper integral because one of the limits was infinity. So whenever we saw that, we had to change the integral into a limit. So I'm coming back to this now, and I'm going to say this is equal to the limit as t goes to infinity, integral 1 to t of natural log x over x dx. That look familiar? We replace the infinity with t, and then do the limit. And we just said that the antiderivative was 1/2. Oh, wait, I forgot my limit. Limit t goes to infinity, 1/2. Come on, Robert. Natural log x squared 1 and t, like that. Oh, man, are you kidding me? All right, limit t goes to infinity. All right, let's plug in. T goes in here, right, first. So you get 1/2 natural log t squared. That's what you get if you plug in t. And then minus, now plug in 1. Oh, natural log of 1 is 0, so this is just 0. And now let t go to infinity. Natural log of infinity blows up, right? This diverges. This goes to infinity, which means it diverges, right? The integral diverges. Therefore, series n equals 1 to infinity, natural log n over n diverges by the integral test. There, little happy face at the end. That only, that took about 20 or so minutes, 25 minutes. Well, right, breathe in, breathe out. I told you that chapter 8 is relentless, right? It's not gonna let up. It's just gonna keep coming. So that's why I said breathe in, breathe out. How about the comparison test? Well, here's how the comparison test works. And I think I can summarize this one pretty clear. Let's see. Let's say that I have a series right here that I don't know what it does, right? And then I've got this other series over here in red. And I do know what it does. All right? Now think about the word for this test, comparison. You're going to compare, right? So what if I told you that this one converged? All right? And then I show you that A sub n is always less than B sub n. What would you say? That this one has to converge. So it's like, look, if I have all these guys in here, and I add them up, and it comes to be a number, and then I show you that all of these guys are always smaller than all of these guys, then doesn't this have to add up to be a number also? What?
What if it goes to negative infinity?
So glad you asked. So there is one condition on this test. We have to be looking at both of these being positive. So the assumption here is that A sub n is positive and B sub n is positive. All right, so imagine I'm adding up a bunch of positive numbers, right? And I add them up and I get a number. Then if those positive numbers are smaller than these positive numbers, then that must add up to be a number. No? Is this not? Are you being just agreeable with me, or?
No, it makes sense.
It does make sense? Show of hands? Make sense? Let's look at two sequences. I'll draw it. Let's say I have B sub n is going to be in black. Here's the sequence, okay? Let's say I take all those little lengths, I add them up, and it comes out to be a number, all right? That's B sub n. And then I tell you I have A sub n is always below that. Then all of those should also add up to be a number, shouldn't they? If adding up the heights of the black ones comes out to be finite, then adding up the red ones should be finite also. Yeah? All right, let me reverse this on you. What if I tell you this diverges? So we don't know what this is. I know what this is and it diverges. Then how can I use that? What if I show you the other way? That all of these guys are always bigger than all of these guys. Then what will happen? This one's going to have to diverge also. So there's two ways that we do comparisons. We look at a series and we say, I don't know what it is, but it looks kind of like something I do know. And I determine whether or not I can say that converges or diverges. Then, once I determine if it converges or diverges, I try and figure out what I'm going to need to show you. Now, this is all stated in the test, but it's hard to read, so I think it's best if I show you an example first, and I have just enough time to do one. Are you ready? Okay. I know you're ready, so here we go. Converge or diverge? Sum. N equals 1 to infinity. N over n cubed hold on. Plus 1. Okay, let's see what we can do in the next 9 minutes with this. All right, so nth term test. So n goes to infinity, infinity over infinity. L'Hopital once, 1 over infinity, goes to 0, doesn't do anything for you. Okay? Nth term test fails. Is it geometric? No. Harmonic? No. Collapsing? Maybe. You might be able to factor the bottom, but I wouldn't even do that. I wouldn't mess with that at all. Okay. Integral test. Would you want to integrate that? Could you integrate that?
Yeah, because you could and then you just use the
What's the u sub though?
n squared.
Yeah, if you had an n squared up top, that'd be nice to integrate, wouldn't it? But it's not n squared up top. So maybe not. How about a comparison? Can you think of a series that looks kind of like this one that you do know something about? So let me help you, because this is our first example. Think about if n is really big. If n is really big, do you really think this one matters too much? No, it doesn't really matter, does it? So, like, if you look at this series, that's pretty darn close to this series, isn't it? Except that little one. So I want to compare these two together. Now, do you know what series this is? What type of series? It's really 1 over what? N squared, which is what type of series? That's a p series, you see? That's a p series. With p being what? P being what? 2, which is greater than 1. So what does this p series do? Converges, doesn't it? Are you all with me? Starting with the series that I don't really know what to do with, I realize it kind of looks like this one, which is something I do know, right? And I know it converges, right? Big C over here. Big C over here converges, right? So that means if I start stacking all these numbers on top of each other, it comes up to be finite, doesn't it? This stacks up to be finite. I'd like for this one to also be finite, which means that all of these guys would need to be what? Bigger or smaller than all of these guys? All of these have to be what? Smaller than all of these in order for them to both be finite. If these are bigger than these, then I can't tell you what happens. You all see the difference? Okay. So what I would need to show you right now, right? What I want to show you, I want to show that a sub n is less than or equal to b sub n. That's what I want to show. Now, what do I mean by a sub n? This is a sub n, and this is b sub n. But there is one thing we have to check for before we can do it. We have to convince ourselves that both of these, the a sub n and the b sub n, are both positive. If they're not positive, if there's a chance that these are negative numbers, then we run into a whole different issue, and that's what the next section is about, which is what happens when these are negative in here. Okay, so are these both positive? Yes. N is positive, that's positive. This, of course, is positive. So I'm going to check. I'm going to go for this comparison test, all right? If I can show you this is true, I'm done. All right? If I can show you this is true, I'm done. Now, how many of you did that homework where I told you to look at those ones where it was the bounded monotonic? I said, watch the video. I said, you won't realize why you need to do this later on, and we'll have to do it. This is why. It's to set up this inequality and be able to work through it. So what is a sub n? N over n cubed plus 1. I need to show that that's less than or equal to 1 over n squared. If I can show that, I'm done. So what did I do in my videos when I had that? Please, not all at one time. I don't like it when you talk over each other like that. It's very rude. What do you do? Yes, I guess you could say that, but you don't need to add.
I'm trying to think, you just put it back into n cube.
N squared here, n squared here. That'll clear out the n squared here. And then you also multiply n cubed plus 1 here, n cubed plus 1. Now, I think in my videos I called this cross multiplying, but what happens when you do that? That's gone. That's gone. So what are you left with on the left side? N cubed less than or equal to, what's the right side? N cubed plus 1. Now what? Nope, just, nope. You're not letting n go to infinity. You stop when you're convinced, and you convince me that that's always true. That is always true? Okay, I was just going to ask you to subtract n cubed on both sides. Subtract n cubed on both sides? And what would you be left with? Is that true? Absolutely, that's true. So what we said is we started with this, and at the end of our work, we came up with something that we all agree on, yes? That means this inequality is always true. Which means that when you when we're stacking up the b sub n's and adding them together, it's finite. And each of the a sub n's is even smaller than the b sub n's, so when we stack those up, it should be finite also. Yes?
So whenever we're going to be using this comparison, we might have to use it in conjunction with another one of the tests. Like, it's how we use a p-series to kind of set it up. Or would it be like one of those simple ones?
It would mostly be simple, but it could be like you're comparing it to a geometric series.
Yeah.
Yes, but I wouldn't ever do something where like you're comparing it to a telescopic that you have to go and figure out what the telescopic's doing. It would usually just be one step back, if that makes sense. Or harmonic, okay? So am I done? No, I'm not done, because now I'm going to conclude. I'm going to say, therefore, the series n equals 1 to infinity of n over n cubed plus 1 converges, I don't know what to, by the comparison test. Done. Again, all the work that I showed in that problem is what you have to show. And you're just going to have to get your hands dirty with the homework. I'll give you what the homework assignment is for this section. You cannot do all the homework in this section yet. But if you watch my videos for the homework, you could probably follow along for quite a ways. Page 453, numbers 6 through 30. That's what I did.
All?
That's what I did, yep, 6 through 30. All. So I think what would be probably a good, fair test on Tuesday.
Did we get this on the test?
That's, man, you know what? I didn't have this on my Cal 2 test. I mean, you know what I'm saying? Like, I didn't have this on my Cal 2 test, so do you think you actually need this? I mean, right now at this point, this is what I'm saying, you would only have on this test up through integral test. I would not put comparison test on there for you. Okay? So if all you had to worry about was n-term geometric p-series and integral and telescopic, I mean, think,
Use half of it.
you tear it in half now. I've told you before, I'm not big on, memorizing. I'm not a memorization person. But at the same time, like, You have to understand these tests. You have to understand why you can use them, how you can use them. Let's revisit that question next class. So my plan, though, is this. Next class, we will continue into 8.3. We'll get into comparison tests. We'll do more comparison tests. Then comes what's called the limit comparison test. Then after that, we get into alternating series test and ratio test and root test. And that'll get us through all the tests. There's no way we finish that next class, though. Here you go. So your test will cover, I know you want to go. I guess you can. I can talk about test next class. Just get caught up with this homework assignment, at least the first, where is it? 6, 7, and 8. 6, 7, and 8 out of this homework assignment are integral test problems. So it even tells you, use the integral test to figure out. So those, every homework assignment I've given you up to this point, and this 6, 7, and 8, that's what would be on the test. And we can talk about the test in more detail next class. Have a good day.